Good morning, guys. Today we're going to talk about the sign on Faraday's law. And this sign really represents Lenz's law. Um, Lenz's law is really a conservation of energy. So basically, Lenz's law states that the direction of the electric current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. We're going to take a look at this example here. Let me get my bearings here, guys. Sorry. And what we have is we have a coil, and we have a magnet approaching that coil with some velocity. Now, according to Faraday, that's going to be a changing magnetic field through a cross section, which is going to give us a change in flux over time. That change in flux over time will induce an EMF in the wires in the coil, and it'll induce a current. So that means that once we induce a current in that secondary coil, we're going to get a change in energy over time, or a del energy over del T, which is going to be equal to I squared R. But that energy doesn't come from nowhere. Energy is conserved. So according to Lenz, there's an induced field, and that induced field must oppose that which induced it. So the bottom line is that that current's going to be in such a direction to form a field that's going to oppose the field that induced it. So you can see here, here's a diagram of it here, and we notice that the current is counterclockwise through that resistor, and we would get a north pointing field opposing that field that's coming in, so a field opposite that which induced it. We're going to look at one more example of this this morning for Lenz, and I like this example a lot. I've used it over the years in my classes, and you have a straight wire, and that straight wire has a current in it that's either increasing or decreasing. In this case, that current's increasing, and that the coil next to the wire is stationary relative to the wire. So according to Ampere's rule, what we're going to get here is we're going to get the current, we're going to get a magnetic field from the wire, and we can kind of see it right in this diagram here, that it's in on one side and it's out on the other. But since that field is changing, according to Faraday, it's going to it's going to give it's going to give a change in flux. And that change in flux is going to induce a current in that wire loop. So we can kind of see it here three-dimensionally. If we take a look right here, I'm going to just enlarge that a little bit right here. Sorry about that. And you can kind of see it here that the induced field is going to oppose that change. So I drew these little magnets on the outside there, and the original field, according to the straight wire and Ampere, is going to have a north pointer up, where the induced field is going to have a north pointer down. And you can kind of see that the two sets are pointing towards each other, which is repulsive. Which is kind of what we expect. We expect to oppose that change in that other field, so we can, as energy is picked up in the loop, energy is decreasing. Energy is decreasing with the the current carrying conductor. And this is what we would really expect right here. Is we expect that the induced field is going to be inside the loop, and the current is going to be clockwise. Well, that's it, guys. So that's a conceptual view of Lenz's law and what's happening there. Thank you so much now.